So let's start with reactions of alkanes, and there's two major ones that we typically see. One is combustion reactions and one is halogenation reactions. So let's take a look at combustion reactions first, and let me just show you generally what the reaction is. You can take any alkane, so I'm not going to draw a specific one, I'm just going to write the word alkane, and so you can think of any alkane you want in your head, and it can go right there. And if you add a little bit of oxygen, what you get as a product is CO2 and water. Of course, this reaction is not balanced, but this is the combustion reaction. Notice in a combustion reaction, the O2, the oxygen, the CO2, the carbon dioxide, and the H2O, or water, always is the same. The only thing that changes is the alkane. And this is something you've seen before. This is what happens in your car engine. If you burn some wood, if you burn any alkane, like at your furnace or on your stove, if you have a gas stove, that's an alkane that comes out and you burn it. So this is basically burning stuff, is what combustion reactions are. So we're burning hydrocarbons. Remember, alkanes are hydrocarbons, which I'll just put HC for hydrocarbon. So it's a hydrocarbon, you have a little bit of oxygen. If you ever want the hydrocarbon not to burn, you can close it up in a container. It doesn't get any oxygen and therefore will not burn. And I'll show you a specific reaction in just a moment to give you an example. A halogenation reaction of alkanes. Now let's recall what's a halogen. A halogen is things like fluorine, chlorine. Remember, these are all diatomic molecules, meaning there's two of them. So it's F2, meaning there's two fluorines to make the molecule. F does not exist by itself in nature. It only exists as two of them together. Chlorine's the same as like bromine and iodine. And if you look on the periodic table, they're all in the same column. And so therefore they're very similar in reactivity. And so those are halogens. So halogenation is putting these on an alkane. So again, if I give you an example, and I'll just use something very simple just to start, but it could be any alkane. If you have an alkane like methane, CH4, so that's an alkane, and we add a halogen, and we can use any of them. I'll just use fluorine as an example. This reacts, if you give it a little bit of heat, this reacts, and one of the fluorines will switch spots with one of the hydrogens on methane. And so if we switch spots, we'll remove one of the hydrogens, so that's CH3, and replace it with the fluorine. So there's CH3F plus, and we used to have two fluorines as a reactant, but now we're going to have an H has replaced one of the F's, and so now we have HF. And if you give it enough fluorine into this reaction, if you get a lot of fluorine in the reaction, all the hydrogens on the carbon can be removed and replaced with fluorine. So if you let this reaction continue and keep adding fluorine, you'd eventually get to the point where you're CH or CF4 if you could just keep putting fluorines in place of hydrogens. So why don't you give it a try? Here is a reaction of these two, of this reaction right here. Go ahead and determine and write down, pause the video and write down what the products are, and then come on back and we'll talk about it. So in this video, in this reaction, we can see that this molecule over here, this big molecule right there, that's an alkane. And if we oxidize it by adding oxygen, this is a combustion reaction. So the products of this are simply CO2 and water. This is a combustion reaction. And notice the products here are always going to be the same for a combustion reaction. It doesn't matter what alkane you start with. Notice we have in the alkane carbons and hydrogens. We have an oxygen out here. And notice in our products, we didn't lose any of those. I still have carbons, oxygens, and hydrogens. Again, this reaction's not balanced, but nonetheless, there are our products. So it doesn't matter how big and complex the alkane is, the products are always the same in a combustion reaction. So now here's another reaction. Go ahead and pause the video, determine what the products are. Once you think you got them, come on back and we'll chat about it. So again, the first thing you have to do is identify what reaction this is, and this is a halogenation reaction. Notice we have an alkane, our same alkane we had in the previous reaction. So we have an alkane, and then we have a halogen. So this is going to be a halogenation reaction, which means basically one of the chlorines is going to switch places with one of the hydrogens. And we have a lot of hydrogens to choose from. And so in this case, you can pretty much choose any one you want, and that's a potential product. Now, some of the hydrogens are more likely to change spots with the chlorine, but for our argument at this point, let's just say all of them are possible, and so therefore any of them is a possible reaction or possible product. So in this case, there's many possible products. For instance, what we do know is, remember this Cl2, if I just draw it a little bit differently, is really this. It's two chlorines bonded together by a covalent bond. And we're going to take one of these chlorines and we're going to switch it with any of the hydrogens we want there. And we're going to switch them. So for instance, I could remove this one and remove that one, and we're going to switch spots. So the chlorine will be there and the hydrogen will be there. Right? That's one spot. I could have also switched it not to there. Let's leave it there. And I could have switched it to this spot right here. That's possible. Or any of the spots. And that would be that's a product of this reaction. Now, if we had a lot of chlorine in the reaction, and I didn't say whether there was a lot of chlorine or just a little chlorine, but if we just let the reaction go one time, this is a possible product. If we added more chlorine, so if we added another molecule of chlorine, right, I would switch one of these chlorines with one of these hydrogens. I'll pick this one right here. So let's go ahead and move this hydrogen and move this chlorine. So the hydrogen will come down here and form HCl, and the chlorine will come up here and form that guy. And we can continue to add chlorines until they are all completely full. All the hydrogens were removed and all the and replaced by all chlorines. So there's a lot of different products here for sure, but if the reaction just happens once, and we have, let me just go back to that, if the reaction just happens once, are we getting there? Yeah. And we get this, and we won't worry about that. So if the reaction just happens once, this is one possible product, but realize this chlorine could be in several spots to make a slightly different molecule. So there's more than one answer for this, but there's definitely some incorrect answers. But this would be one correct answer where you have two products. You have the alkane with a chlorine on it, and you have no longer have a chlorine atom, you have a hydrogen chloride, the acid. Now with alkenes and alkynes, we have 4 different reactions that can take place. Hydrogenation, halogenation, hydrohalogenation, and hydration. And a key thing to know about reactions of alkenes and alkynes, remember alkenes have a carbon-carbon double bond and alkynes have a carbon-carbon triple bond. It is there that all the reactions occur. It occurs at the carbon-carbon double bond or at the carbon-carbon triple bond. It doesn't matter how big the molecules are. Focus on that carbon-carbon double and carbon-carbon triple bond. That's where the changes are going to occur. And with all these, what we're going to be doing is, you'll notice we're breaking the double and triple bond, and we're adding atoms to it. So we're going to take 2 things and combine them together to make one thing. So it's an addition reaction. Like 3 plus 4 equals 7, we took 2 things, 3 plus 4, 3 and the 4, and we combine them together to make the 7. In this case, we're going to be taking 2 molecules. In each of these cases, we're going to be taking 2 molecules, combining them together to make 1 molecule. While combining them, we're breaking those double and triple bonds. So let's take a look at the first one. That's hydrogenation. Hydrogenation is hydrogen. Notice that's part of the word. So we're dealing with hydrogen here. Again, just like chlorine and bromine and so forth, hydrogen exists in nature as H2, or H bound to H is another way to look at it. And what these can do is we can take any alkene or alkyne we add the hydrogen to it, and what we're going to get is an alkane or an alkene. So by doing this, the alkene will become an alkane. The alkyne will lose one of the bonds. It'll go from 3 bonds to 2 bonds. And notice with the alkene, we go from a carbon-carbon double bond to a carbon-carbon single bond. We're going to break that one of those bonds. In halogenation, again, we start with an alkene or an alkyne, and I'm just abbreviating there. It's the same as on the first one. Now, halogenation, we just learned just a moment ago on all the halogens, F2, Cl2, Br2. So we can take any halogen we want, and just as an example, I'll use Br. And what do we get there is we get a dibromo, so 2 bromines on an alkane, or dibromo, 2 bromos on an alkene. Again, the alkyne, which is a carbon-carbon triple bond, will be removed and one of those bonds can be broken to make an alkene with carbon-carbon double bond. Or we take a carbon-carbon double bond and we break one of those bonds to make a carbon-carbon single bond. And the bromo groups are added to it. Hydrohalogenation, notice hydro, that's H, and we know what halogens are. And so these would be things like HBr or HCl or HI or HF, any of those, because it has a hydrogen and a halogen. And it's the same. We can take our alkenes and alkynes plus, again, I can use any of them, but that's an example of one. And so in this case, I would get a chloroalkane, so an alkane with a chloro group on it, or a chloro with an alkene, depending on if I started with an alkyne or an alkene. In a hydration reaction, hydration we can recognize as water. And again, we can take our alkene or alkyne, we can add a molecule of water, and what we get here is an alcohol, or we get an alkene with an alcohol group as well on it. So it's sort of a mixture. And I'll give you a couple of examples of each of an example of each of these. So here's one. So go ahead and give this one a try based on what we just talked about and see if you can come up with the product of this reaction. When you think you have the product, come on back and we'll chat about it. So in this reaction, we first take a look at what we have, and notice we have a alkene right here, right? I can see it's an alkene because I see this carbon-carbon double bond right there, so I know I have an alkene. There's a lot of stuff hanging on it, but nonetheless, that's an alkene. And then I'm adding hydrogen to it. So this is a hydrogenation reaction because I'm adding hydrogen to it. And remember, this is an addition reaction. So we're going to take this alkene and add on the hydrogens. And I told you, when you do this, focus on that carbon-carbon multiple bond, that carbon-carbon double bond in this case. So we're going to focus everything right here. Now, because we're adding things to it, we're not going to subtract anything. So the things currently hanging on the carbon, those 2 carbons involved in the double bond, meaning this methyl group, that will still be there when we're done. This will still be there when we're done, because remember, we're adding, we're not subtracting. This will be there when we're done, and all of this will be there when we're done. So really, we can just kind of, in our heads, just kind of remove that from our brain for a moment, at least mentally, and we're going to just focus on that carbon-carbon double bond that we did not square up there. Now I'm going to remove the squares just to clean this up a little bit, but just mentally. So I'm going to focus just on that carbon-carbon double bond. And what happens is that we're going to add it. So let's take these hydrogens. Now remember, this hydrogen is really that, and we're going to float it on over to here just so we get it a little bit closer. So I'm going to put them right here. So we're going to line it up. And all we're going to do is we're going to break that carbon-carbon double bond. And we're going to break this hydrogen-hydrogen bond. So I'm going to move this bond to here, move this bond to here, essentially, and we're going to create new bonds. Let me go ahead and erase the old bonds, and let's put the new bonds in. And the color here doesn't matter. I just happen to have a purple pen on me. That's what it is. So now you can see the new hydrogens have added on. And we now have a carbon-carbon single bond where we used to have a carbon-carbon double bond. And so here now we have an alkane. So we've made an alkane in this process. What's the other product? Well, there is no other product. We added all of that we added all of this to the alkene to form the alkane. And so that's our product. So we have an alkane as a product, and the two new hydrogens are added on. So let's try this one. Here's another one. So go ahead and determine what the product of this reaction is. So go ahead and pause the video, then come on back when you're ready, and we'll chat about it. So in this one again, I have an alkene shown in red here, the same one we had in the previous reaction. But this time we don't have a hydrogen molecule, we have a hydrohalogen. So this is a hydrohalogenation reaction. But you'll see it's pretty much the same as the hydrogenation reaction with the hydrogen atom. Again, let's just focus on where the reaction is going to occur, and the reaction is going to occur right around that carbon-carbon double bond. So let's go ahead and take this hydrohalogen, and we're going to move it on over to here. So we're going to remove it from there. We're just going to slide it on over here to get it close to where it wants to go. And then we're going to go ahead and start breaking some bonds. We know we're going to break the carbon-carbon double bond, at least one of them, and make it a single bond. So we'll move this bond to here, and we'll move the bond between the hydrogen and the chloride over to here to form two new bonds. And let me go ahead and erase what is now gone. And notice here again, now what we have formed is the product. So it's a single molecule as the product. Notice we took the alkene, we took the hydrogen halide, and we just combined them together to form one molecule. So there's only one product. And we now have an alkane as our product, and the alkane does have a chloride on it. Now, it doesn't matter which way I put the hydrogen and the chloride on. I could have done it the way I did it here, or let me erase a few things here. And let's say instead of attacking like this, I put the hydrogen here and the chloride over here. That would move the chloride to a different carbon, so it makes a different product. So although we add two things together to make one molecule, we could have made a couple of different molecules, either the chloride on this carbon, either the chloride on this carbon or the chloride on this carbon. Either way, we still made an alkane with one chlorine atom on it. So here's another one to try. You can go ahead and give this one a try, determine what the product is, and then come on back and we can chat about it. So again, we see that we have an alkene here with a carbon-carbon double bond, and so we know that we're probably going to be going after that carbon-carbon double bond. That's where we're going to attack, and that's where the reaction is going to occur. It doesn't really matter what else is on. Notice that in all these reactions, we don't really care what else is on the carbon-carbon attached to the carbons of the carbon-carbon double bond. Those don't get changed in any way. Here we have a fluoride ion, and fluoride, and we can redraw it like that, where it's two fluorines connected by a covalent bond, and we're going to move that guy right on over to here, and we're going to have the reaction go. And in this case, again, we're going to move one of the carbon-carbon double bonds on down, the bond connecting the two fluorines over here. So we move those two. So let me now remove what is now gone after moving those electrons to a different spot, and we get that guy. And again, since the two fluorines are the same, it doesn't really matter which way they connect to the carbons. There's always going to be one fluorine on one and one fluorine on the other carbon. And so there's one product in this reaction. Again, we've added two things together to make one thing. And so that's our product. Notice that it was an alkene. It lost a double bond and went to a single bond. And so now it becomes an alkane with two fluorines on it, or two halogens on the molecule. Okay, we'll do one more. Go ahead and determine what the product of this reaction is. I just put the arrow over here. Determine what the product of this is. When you think you've determined what the product is, come on back and we'll chat about it. So in this one, now this is a little bit different this time. Now we don't have an alkene, we have an alkyne. Notice the carbon-carbon triple bond in there. But it doesn't change our strategy at all. It's a little bit different, it looks a little bit different, but keep the method of what you're doing the same. We're also going to be adding a molecule of water. So this is a hydration reaction because we're adding water. Water's hydration. And so we're going to change this molecule, this water molecule, to make it look ready to add on to our alkyne. So again, we're going to be adding it on. Water likes to break apart. Notice there's not two atoms here, but three atoms. But it likes to break apart between the oxygen and one of the hydrogens to form a hydrogen and a hydroxyl group. And so we're going to go ahead and move that on over to here. So we'll put a hydrogen here, bonded to a hydroxyl group here. But at this point, again, we just do it the same way we've been doing. It doesn't matter that it's an OH or an F or whatever. This is what we're just going to work with. And we're going to do the same thing as we've done before. We're going to move one of the bonds of the triple bond, so not two of them, just one of them. We're going to move it on down to here, as we've done before, and we'll move the bond connecting the hydrogen and the oxygen on up to here to go there. Let me go and erase what is now gone after we move those electrons. And that is what we get. We get that molecule right there. Notice this is got a carbon-carbon double bond, so it looks kind of like an alkene, but it also has an OH group, so it also has an alcohol look to it. So it's basically an alcohol and an alkene. Now, we could have put that on in the opposite direction, meaning I could have not ended up with a hydroxyl group on the one carbon, but put it on the other carbon. So we could have basically had this look. Let me get my 3 bonds back. There's my 3 bonds. And just as before, because the two atoms that are connecting to the carbons of the triple and double bond are different, there's 2 different ways in which it could go on. But still the same thing happens. We move one bond down to here, one bond up to here to form these 2 bonds. And let's get rid of what has now been moved because of that reaction. And we get that. Notice in this case, this is also a possible product. But notice in this case, the OH group is now on a different carbon than it was previously. Now, if there was enough water around, because now we have an alkene, it could undergo the reaction again. And so we could actually have another molecule of water. I don't know how much space I have, but let's take another molecule of water. And in a second reaction, because there's an alkene still there, I'm having trouble getting that. There we go. It's not wanting to do it. I don't know why. But you can see that those 2 lines there, that's supposed to be an H. It's just not wanting to connect for some reason. Oh, there we go. And one of the bonds will move to here. One of the bonds will move to here. So we'll connect those. Let's erase what's in between, or what was lost in that reaction. And we get that. And that bond should be connected to the oxygen, not the hydrogen. And so we get that. And again, that one could have gone on either way. So the OH group could have ended up on the carbon it's showing it's ended up on, or could have ended up on this carbon. So it could have gone either way. So in the end, because this reaction happened twice, we could have the OHs on the same carbon or different carbons. Both are possible and both are correct in terms of being able to form. So both will form. They just might not form in the same amounts. But nonetheless, both will form. So this is a hydration reaction. In this reaction, I showed you what it looks like with a triple bond and a double bond because we did both. So if you started with a double bond, the same thing would happen. We'd add a molecule of water and make an alkane with a hydroxyl group on it, which is essentially an alcohol.